let me introduce Professor Rückmann from Bergen University in Norway, as I said. I remember we met for the first time in 1998, perhaps in Washington, in that conference in Washington, and 1 year later, you were a member of the thesis committee of Juan Parra, my colleague Juan Parra. And indeed, from that time, we keep a very near relationship with our group. And he has also participated as a member of the committee of some PhD of our group. Well, he has around 90 papers in the most prestigious journals as mathematical programming, science, María Josefa analysis, JOTA, etc. And his fields of interest are parametric optimization, semi-infinite programming, mathematical programming with complementary constraints, and among others. And just to finish, let me point out that he is an excellent speaker, as you can check in a moment, because I think he always tries to pay attention to the geometrical ideas which are behind the concepts, which are usually quite difficult. So it's a pleasure to have you here, and we are yours. Thank you.
Yeah, thank you very much for this. I never got such a kind introduction. Thank you very much. And I think we met the first time in
Yeah.
Okay, so my talk is about strong stability of weakly non-degenerate stationary points, and it is based on joint papers together with Daniel Hernandez Escobar. He is an ex-PhD student of mine. He's Cuban. He's now in Uppsala in Sweden, and Harvard Pilsner from Aachen University. Here are two of the papers on which this talk is based. So I have to learn this now. This one, okay. Okay, so here's a short outline about that, what I'm going to talk to. Perhaps let me only say something here. We will talk about stationarity in basic Lagrange vectors. Basic Lagrange vectors are a generalization of the extreme points of the Lagrange multiplier set. And the other things I will explain with more details now. So what is a class of problems I'm going to look at? A mathematical problem with complementarity constraints is defined in that way. We minimize the function with respect to a feasible set. And the red one here is the difference to the standard nonlinear programming problem, which is defined by equalities and inequalities, finitely many or infinitely many. And here we have this minimum characterization. So we have pairs of function R1, S1, R2, S2, and so on. And we say that feasibility means that the minimum of them is equal to 0. L is a finite set, as here this index set L, and we assume C2, but sometimes it's only C1. We will not specify this later on. That means our problem, we were talking about strong stability, so that means strong stability with respect to the function which define the problem. So we see F is our objective function, and R and S are the two constraints where we take the minimum over. Whereas, geometry, if we have R1, if we have one pairs, R1 and S1, we say if the gradients are not 0, we can take the gradients as new coordinates, and then locally it looks like that. Okay, so R1, S1, and then we see the feasible set is characterized by these two parts, and what we see here is MPCC as a complementarity constraint. The problem is here, the kink. There non-differentiability appears, so we cannot use the machinery of differentiability, which is standard in nonlinear programming. Here we have to do something. These are the points where we always have to look at. Yeah, so if only one of them is 0, then we are here or here, and this locally is like standard optimization problem. We have one equation, and the other is not active. Yeah, the point where something is happening or where we have to put more attention on is on these king points here. Okay. Okay. So the first two I just said, there are many applications. What we are doing here is strong stability, looking at strong stability for MPCC. So what is strong stability? Strong stability is solution. I would say something what means solution here in a moment. Strong stability refers to uniquely existence of a point of each sufficiently small perturbed programs, where we allow perturbations up to second order, for the function itself, or for the first and or second derivative. And a little bit more, that not only we have existence and uniqueness for each locally, for each sufficiently small perturbed problem, but also that the solution, which is uniquely determined of the perturbed problem, depends continuously on the perturbation. Yeah, the smaller the perturbation is, the nearer the perturbed solution is near to the original solution. And of course, you can say these are nice. These are. These are well-posed properties. Yeah? Existence, uniqueness, and continuous dependency on the perturbation. And you can define this, but you cannot handle this. You cannot check it.
Sorry, sir.
Yeah.
Which is the difference with Tikhonov or Postness?
Oh, I don't know. I'm not.
Okay.
I don't know. I mean,
I think that also uniqueness and continuity is required. With Halaman, I don't remember.
So I don't know.
I thought it was something else.
Yeah. I mean, what I said to Tikhonov, he put some, let's say, epsilon squared, is more important.
Yes.
Yeah, for example.
Another, perhaps is not so general concerning the perturbations. Do you consider any kind of perturbation?
No, we do not say that the perturbations depends on the real parameter. The parameters
Yes.
are the functions. So we are in an infinite dimensional space.
Very clear.
Yeah. Okay, so but the point is you can say that, you can define it topologically, but you cannot manage it. You cannot decide is a given point strongly stable or not, because you don't know what happens when we perturb it. That means the challenge here is to write this down in terms of the functions. For example, take the Hessian into account or something like that, and we come to this in a moment. This is a challenge, how to characterize algebraically, in a form that you can check theoretically, strong stability of a solution. The point is that what is a solution here? So in nonlinear programming, in the standard case, we consider a stationary point as solution, as in the sense of when does a stationary point is strongly stable. In mathematical programming with complementarity constraints, we have several concepts of stationarity. And then we have always to ask, what does it mean for an A stationary point, an M stationary point, an S stationary point, C stationary point to be strongly stable. So last year I was here to give a talk about C stationary points and their strong stability. This time I will focus on M and S stationary points here. Okay, so let me go very short to history. Kojima in 1980, 45 years ago, he introduced this term, strong stability, almost at the same time as Robinson introduced strong regularity for generalized equations, which under some special assumption is the same. And he characterized strong stability. I don't know what this is here. The pointer. Okay.
On the screen, but it is great.
Yeah, sorry, yeah, okay. So he introduced strong stability for a stationary point, and what he did is, topologically, that's only a definition, and then algebraically we come to that what he did there to characterize strong stability under linear independence constraint qualification and under one design formalism constraint qualification, and then it was not clear what happened if it's not a fulfilled one design formalism constraint qualification. This was then shown much later, 2006, and for semi-infinite program in 2012, that we need MFCQ for strong stability. And then you see here also, for MPCC, there's something done already for C stationary points, what I talked last year, and also for an M stationary point. And what we do here is written here in blue. Here we will use a new characterization, which is called weak non-degeneracy, which I will introduce in a moment. Okay, so far the introduction. Yeah. Some notations and basic results here. As for a vector, we look at the index set of components which are 0 and non-zero. And we have here V is a neighborhood of X bar. We aggregate in that way. And to apply the concept of strong stability in order to say, what does it mean that the perturbation is sufficiently small? We need something which is same norm introduced also from ethics by Kojima. I abbreviated here only to say the same norm refers to perturbation of the function value of the first derivative and of the second derivative. Okay? What we will use here is a general form in the form of a generalized equation in order to characterize or to include the several stationarity concepts for MPCC. So we write this down in that way, and so find a point such that this is fulfilled. This is our Tucker condition in the standard case. Yeah? So on the left-hand side we have the gradient. Not so. Where is it? Here. So we have the gradient of the objective function, and then we have here the gradients of the constraints, and these are the Lagrange multiplier vector. And this Lagrange multiplier vector is taken from a cone theta. This theta here is a cone mapping, and the different cones refer to different stationarity concepts. Yeah, so we can cover with this generalized equation here several concepts, and of course also for NLP we got here exactly the Tucker conditions. Okay, and then we identify here our problem as P is superindex theta FF. So F is objective function, small f, and big F, capital F are the constraints, and the theta refers to which kind of stationarity are we considering. As you have seen in the beginning, I will refer to M stationarity and S stationarity, so that means then we have corresponding thetas here. Okay, then we can generalize standard definitions from linear programming. We consider our problem here in P as again, this means we are looking for stationary points of a certain kind, that is in theta fixed, FF, and the point X from Rn. We say it's John point and stationary point in the way, always in mind, what is it in the standard case. Then we have an idea about what we have here. Also, left-hand side is the gradient of the objective function. Right-hand side are the gradients of the constraints, and theta refers to the corresponding Lagrange multipliers. Okay, and this theta is then the Lagrange multiplier vector or Lagrange vector. You have it here, and it is clear that we have exactly there exists a Lagrange vector, so that means this set here is unequal to 0, if and only if we have a stationary point. But if it boils down to nonlinear case, it is that what we know. There is no surprise. Okay. So this is what I just said. So when we choose theta, accordingly, we can cover with this generalized equation all the stationary different sets we know. And we can also make it general to the linear independence constraint qualification and to the Van-der-Waals constraint qualification, always depending on the corresponding choice of capital theta here. So here we have theta, and here's this. Here's a little small trick in this definition, which is mentioned here or referred to in the last line, namely that all the people from convex analysis know that, of course, the span of the empty set is 0, the smallest subspace, which we have for the which contains the empty set. Okay. So here are some technical things, properties. Here. Also for nonlinear programming, these generalized LICQ, generalized MPCQ are the well-known constraint qualifications. We have that this MPCQ holds for any case whenever we have this is the empty set. So if there is no, we do not have stationarity property fulfilled here. And we also use as synonymous that the constraint qualification holds at the point x if it holds for the constraints here. Or you can say for the problem. No, but the constant qualification depends only on the constraints, not on the objective function. And then also we will do this very fast here. The measure for perturbations depends then, of course, on the semi-norm we have introduced, and we also define here the neighborhood of a code p bar on the neighborhood which depends on the radius delta. So these last things here, the blue ones, are for how to measure perturbation locally. Okay? All right. Now we are almost done here with the pre-definitions. So this first definition of strong stability here is taken from Kojima, or generalized from Kojima. Yeah, so we say it is strongly stable if there exists a neighborhood with a radius d delta bar, such that for all smaller radius delta between 0 and delta bar, there exists a number, and for each corresponding problem we have exactly one stationary point, and that depends continuously on the perturbation. So you see here, we have here the neighborhood with respect to radius delta bar, and here with delta, and there must always be exactly one stationary point. And we also use weakly stability, which is not the main point in this talk, but here we have only delta bar. So here we have no continuity on the perturbation. We have only that it is uniquely determined. Okay? And now, what was Kojima's, in my opinion, main merit in this context? He characterized algebraically strong stability. Okay? And the special case for the MFCQ case, yeah, so if we have LICQ, this is already characterized in the literature. But under MFCQ, but not linear independence, we have the following: strong stability, the first property. Here, this is strong stability, and this is equivalent to say the following: for all extremal points of the Lagrange multiplier set, it holds that the hashing of the Lagrangian respected to the tangent space is positive definite. That is a algebraic characterization of strong stability. And we know that this set L of this one, the Lagrange multiplier set, is a compact polyhedron under MFCQ, and he says something only about the extremal points, about the vertices. This set. Yeah? So the characterization is here about the vertices of the Lagrange multiplier set. And this gives us already an idea, we will see later, that for our case, we have that the set of Lagrange multipliers need not to be convex. So it makes no sense to talk about the vertices of the Lagrange multiplier set. So we have to generalize in some way. Yeah, so Lagrange multiplier set, but what does it mean? What is in the NLP case? The extremal point set. It doesn't exist. Yeah. We will see how to solve this problem. Okay, now let me define basic Lagrange vectors, which are this generalization, what I just said, the extremal point set. So we call it basic Lagrange vectors, and we will define it in a moment. So we define here some index sets, and we see that this is the these are the indices which belong to RL is equal to 0, but SL is positive. Remember, the minimum of both must be 0. So one of them is 0, and here we have the other way around. And the interesting case is, if we go back to this picture, the king cases. Yeah, what happens in the origin? There, where both are 0. The index set IRS here. And I recall here M stationarity and S stationarity. The difference, the first two things are the standard things here. I have problems with this. The standard things, also the gradient with respect to x of Lagrange is 0, and we have some complementarity constraints here. This is the same for S stationarity, but the difference lies in the blue part. Here we have that rho L and sigma L are the corresponding Lagrange multipliers in the Lagrange function. And they must be both positive or one of them is equal to 0. And here, S stationarity means a little bit different things, namely that we have that here. Okay, so it means M stationarity plus S stationarity here. Okay, and this is only technical, I will not go here into detail. Remember what I said, when we are looking at the generalized equation, we can cover these different concepts of stationarities for MPCC. And here it is explained how that works. So the difference lies in the difference in the definitions of this theta, big theta. Yeah? So different thetas refer to different stationarity concepts. And here is the one for the M stationarity. And you see this definitions here, this one and this one, refers, of course, M stationarity refers, of course, to these properties here. And analogously, these properties imply the definition of capital theta. Okay? And here's already one thing which is different to standard optimization, namely this theta m. Theta is a cone mapping. Yeah. Is closed, but theta s is not. Yeah, so if the cone is not closed, one has to take care about this special situations. Okay. We have the following now. These are two new definitions because we changed it because of the reference report. We had only the first one, but then we have to change it. That's why it's appearing here as well. The generalized LHCQ is, of course, for both stationarity concepts under observation, M and S stationarity here equivalent to the LHCQ MPCC condition. That means all the constraints of active, all the gradients of active constraints are linearly independent. And okay, so we say this one, important is that here. M MFCQ implies S MFCQ. Well, we have seen that in the definition. And also, here comes now the set of Lagrange multipliers into play. The the Lagrange multiplier set for S stationary points is a subset of the Lagrange multiplier set of n stationary points. And we can see, where we have proved, that MMFCQ and SMFCQ, as a generalized MFCQ now applied to M stationarity and S stationarity, are necessary for strong stability of the points. And we will now focus on strong stability and weak non-degenerate points, which is defined here. Perhaps let me explain it with more words. So if we are looking at the Lagrange multiplier function, the Lagrange function, then we have, in the case where both are active, we have corresponding Lagrange multipliers, O and sigma. And in the non-degenerate case, both are assumed to be positive, respectively non-zero. We say that as non-zero, then we are talking about non-degeneracy. And we look at a more weaker condition. We say it is not possible that both are zero, but at least one of them is non-zero. So that means, if we assume weak non-degeneracy, then that means that the corresponding Lagrange multipliers, at least one of them is non-zero. Okay? And having this in mind now, let us come back to the set of Lagrange multipliers L, as PC refers to S stationarity, and M refers to M stationarity. And now comes that here into play, what I mentioned before. In the standard case, this set is a compact polyhedron, and you can work with this using the machinery of convex analysis. This is not the case here, because L for S stationarity, here, we have convexity, but not for M stationarity. So that means the question is that here, how to use extreme points or how to use a certain standardization of extreme points. And we did this here, and we call it a basic Lagrange vector. This is very technical. I will not go here into details to discuss this here. But then we see, remember that this first set here is convex, so we can talk about extrema points. But the set LBB, the basic Lagrange multiplier, can now characterize them that way. So we have a relationship between the Lagrange multiplier set for S stationary points and for M stationary points. And we have more, namely now our weak non-degeneracy comes into play. And the next point here, if we have weak non-degeneracy, then we have this. Okay, so both sets are equal, if and only if we have this inclusion here. And both sets are equal is interesting because one is convex, and then the other ones are. Okay, and we have here another property, another equivalent relation. This minus here is too much. The latter condition does not necessarily imply that both are equal, which is shown in the next example. So I will skip this example because we are already
don't worry about the time because we have started 10 minutes late.
Yeah, okay, then I go to the example. Okay, so example 1, let x bar be point under consideration, and we associate, or we are looking at the following blue problem here. Yeah, so here. Okay. And then we can see that the set of basic Lagrange multipliers refers to the extreme point set of the Lagrange multipliers for the corresponding S stationarity set. And this is that here. But, okay, so here, boom, boom, boom. Therefore, the blue thing is important, both are not equal. And also, x bar is not weakly non-degenerating. So we have a point, we have a pair of Lagrange multipliers that both are zero. Okay, we can say something. The question now is it only a definition, pathological definition? No, it is not. There are existing basic Lagrange multipliers. And you can see here an equivalent relationship to the existence of basic Lagrange multipliers, which is given here. It is also pretty technical. Okay, but it is let me say that again to remember the big picture. These basic Lagrange multipliers are the generalization of the extremal points, which we know from the polyhedron of the Lagrange multiplier set in nonlinear, standard nonlinear programming. Now we come to a necessary condition for strong stability, which is the Magasin-Formwitz constraint qualification for M stationary points. And what we assume weak non-degeneracy for the point under consideration, which is S stationary. And what we are using here to characterize this or to show this, we call a relaxed problem, which was originally by Schlegel-Scholtes in 2000 introduced. P bar relaxed, or L. It is a perturbation of it's a standard nonlinear program, which you can see here. So you see that this function, this set, not only depends on the functions, it depends also on the points. Yeah, we have here x bar, the point under consideration here, x bar. That is our point under consideration. That means this index that's here depends on x bar. So it means if we change the point, this relaxed problem looks different in general. Okay, let's see what I just said. As a P relaxed does not depend only on the functions, but also on those describing P bar and on the point x bar. And it is easy to see that the set of Lagrange multipliers of the next problem is equal to the set of Lagrange multipliers for the S stationary point. And then we can here define, or can consider the following lemma. If we have S Magasin-Formwitz constraint qualification, then for all sufficiently small perturbed problems, we have this here. So that's a set of stationary points for the relaxed problem. Stationary then always referring to the type of stationarity, here is S. Stationarity. Locally intersected by a local neighborhood is a subset of the corresponding stationary points for P. But, as it says here, this inclusion can be strict. So it means this is a real subset of the right-hand side. And that means if the left-hand side is referring to strong stability, the right-hand side need not to be strong stable. There could be another second strongly stable, second stationary point. And that is here written in blue at the end. Strong stability of x bar for the relaxed problem does not imply strong stability for P bar. And you can see this here on the second example. This I will skip now and come as a third one. Okay. We look at the following theory now. If we assume S stationarity for x bar and the problem P bar, and if x bar is weakly stable in one of these two sets, then we have that x bar is also a S stationary point, a strongly stable stationary point for the next problem, and we have that these two sets are the same. However, the boundedness of L P bar Cm x bar does not imply the Magasin-Formwitz constraint qualification. Remember what is the case in the nonlinear standard program? This is equivalent. No? Is an alternative theory. Magasin-Formwitz constraint qualification is if and only if this is the set of Lagrange multipliers is bounded. This is not the case here for MPCCs, And we can illustrate that by this example 3 here. You see it here. MFCQ does not hold, but we have the set of Lagrange multipliers. It's a convex whole of 2 points. Is bounded. Okay, so we go down to the main theorem of the section. If x bar is a strongly stable stationary point with respect to S stationarity, then M MFCQ holds at x bar for our problem. Yeah, also strong stability with respect to S stationarity implies that M MFCQ. So here's always a relationship between these two stationarity concepts. And let us finish. Now we come to that what I intended to explain from the very beginning on. The challenge is always to characterize algebraically strong stability. Yeah? Also, how can we formulate conditions, for example, on the Hessians restricted to the tangent space and so on, which decide whether or not the point is strongly stable. We assume a weakly non-degeneracy for our S stationary point here under consideration. Then we have the following situation. Assume MFCQ, and we assume that both Lagrange multiplier sets are equal. We discussed this condition in the previous chapters. Then we have corresponding neighborhoods of x bar and of the problem, such that we can say something about the Lagrange multiplier sets. Here our VLX problem comes into play again. And also we have it with respect to the set of stationary points, of course, locally. We have always to intersect it with the corresponding neighborhood V bar. Okay? And then we will get these two characterizations. The topological one, which is again not, we cannot handle this, but it is a definition, of course. And in the next slide, then we will see the algebraic characterization of strong stability. As the following 3 conditions are equivalent, we have that the point is strongly stable with respect to S stationarity, equivalent to S strong stability with respect to M stationarity, and we have the third condition, which consists of 3 parts. X bar is a strongly stable point with the relaxed problem. These 2 sets of Lagrange multipliers are the same, and in monozyme form its constraint qualification. X bar holds for our problem P bar. Now, the tangent space is defined in the standard way, and it allows us now to come to the algebraic characterization. This is really what we wanted. The challenge is to find algebraic characterization here. We assume that MFCQ, but not MPCC LICQ is fulfilled. So again, MPCC LICQ is already covered in the literature. This case for linear independence constraint qualification. For us, the case is interesting when we have this MFCQ here. And then we got 5 conditions which are equivalent. So the first 2 say the point under consideration is strongly stable in both concepts for S stationarity and also for M stationarity. And now comes the algebraic characterization, namely that P bar L has convexity for the Lagrange multiplier set. So we can say something about the external point set. And then we say the Hessian of the Lagrangian with respect to the tangent space is positive, definite. This is equivalent if we now take into account our generalization of extremal points, namely the basic Lagrange vectors. Remember, this was a set which is not the right-hand side here. It's coming. Also, here. So this set is non-convex. No, this is convex, but this set for Lagrange multipliers for M stationarity is non-convex, and here we use now our concept of basic Lagrange multipliers. And then we say for all rho bar sigma bar extremal point set, it holds this positive definiteness condition here, and is similar in number 5. So the main point here is to have this algebraic characterization, and it looks like that. Very similar to the schema, when we say hashing of the Lagrangian restricted to the thing space positive definite. Of course, it is a little bit different for schema because we use here basic Lagrange factors, not the extremal point set, but positive without positive definiteness in the MFCQ case, not under LSQ. That is a different story. In the MFCQ case, is exactly that. And with this, I finish, and thank you for your attention.
Thank you very much. Is there any question or comment?
I would like to ask the question. You know, we are from time to time interested in problems of disjunctive optimization. In particular, I think I would like to know your opinion if this framework of MPCC could be appropriate for studying the stability of the Pareto front in a multi-objective problem, or in general the stability of a union of sets. For example, the problem of minimizing the distance to a union of sets, or this kind of structure where you have unions like this. Do you think we could find some application to the stability of Pareto front, or
What was the last word? Pareto?
front?
Yes, okay.
Okay.
As spontaneously, I don't know. What I think is for the disjunctive approach, that is what I wanted to discuss with you.
Okay.
But not about strong stability.
No.
Another thing. I also saw in this disjunctive approach. But with respect to your question, so the union of things, which appears, for example, in Java as in programming, for example, you have a union of things, union of sets. I don't know. I don't know what here is strong stability.
But we can
explore.
Can explore, because from time to time we have to face, for example, the n sets we are dealing with a union of convex species. So
so then we can only, if you look at the distances, then you took the distances to each of the sets.
Yes.
You took the minimum. Or
yes. That's the point. The point. Okay.
Is there any other question? This is a silly question, but in this stability notion, I think you are perturbing the complete, fully perturbing the components S and SR and R by different function, and you are measuring the perturbations through this seminar, no? The maximum of the images plus the first derivative. But sorry, I don't remember. This maximum is taken in a neighborhood of the point?
Yes, it is local.
But this neighborhood doesn't play any role regarding this characterization, or you can take any neighborhood of the point? Or
no, the statement, there is a neighborhood. There is.
Because
so what happens outside? And then these properties here are fulfilled in a point, and that means positive definiteness. Then it's also
this is the
It
best.
could be in the neighborhood, but we don't know how big the neighborhood is. It's always restricted, it's local consideration.
And for instance, if the perturbations are not completely free, but I don't know, for instance, linear perturbations, and then you measure the size of perturbations, some
You mean if
more particular norm or something like that. Do you think that you could obtain some quantitative, not only qualitative, but quantitative results, Lichit time, for instance, results or something like that?
you mean if you only consider linear perturbations?
For instance, linear or with some particular setup.
So there is in nonlinear programming, in some cases, Kojima made a statement about in this direction that you say if you are not strongly stable, you always find linearly perturbed problem where you have two or none. So where you can see that it's not fulfilled strong stability. But I don't know if this is the case here. Yeah, that could be.
Yeah.
Yeah, because that is then for technicalities and proofs could be important to say, okay, it's not strongly stable, and then I know there exists a linear perturbation which shows this non-stability property. That's possible.
Thank you so much.
Okay, thank you. So something from online.